Hey, welcome back to Fat Mama Physics. Man, these are so many examples. Okay, let's go. 8 and 9. Let's do it. Okay, 5.1b, this is electric potential energy. So, let's use green just to differentiate the colors. Okay, the centers of two alpha particles are held 2.5 times 10 to the power negative 12 meters apart when they are released. Okay, so two alpha particles together, then you let them go. We want to calculate the speed of them when they're 0.75 meters apart. So, first of all, what are alpha particles? Alpha particles are really just helium nuclei, okay? And helium nuclei is made of two positive charges and two neutrons. So, in terms of the charge, we have two protons, or two times the elementary charge, okay, for the charge. So that's the Q. But for the mass, this is going to be to be more precise, it's actually 2 times the mass of a proton plus 2 times the mass of a neutron. Okay, so that's just what we'll have to deal with later on. But let's try to conceptualize what is happening here. For the alpha particles, I'm just going to use that alpha symbol. So at one state, there's an alpha particle here, there's an alpha particle there. They are only 2.5 times 10 to the power negative 12 meters apart. And then after we release them, they're going to be further apart. They're going to be over here, which is 0.75 meters apart. Okay, so if they're close together, remember, an alpha particle is made of it's really a helium nuclei. And since they're positively charged, they're going to want to repel one another. So they're going to, they start off with a high potential energy state, in which once we release them, that potential energy is going to get converted to kinetic energy when they are further away. So really, it's we have to look at the difference in the potential energy of these two states. So, let's see how much we can zoom in here. Okay, so we're gonna get, I'm gonna use blue here. We're gonna get potential energy here, initial. Ooh, that's gross. We're gonna get we're gonna get potential energy here between these two alpha particles, okay? And then that's gonna be our initial state. We're going to have some final potential energy state here, and in which the kinetic energy to begin with, since they start at rest, is going to be 0 joules. And the kinetic energy here of the two alpha particles, we don't know. That's what we want to find out. But we do know that the potential energy will get converted to the potential energy is going to get converted to kinetic energy. So we just need to find the change in potential energy. Keep in mind though, both alpha particles are free to move. So only one of the so the kinetic energy that we find is going to be for both alpha particles and not just for the one alpha particle. So let's write this out over here. So if we write the conservation of energy, which I'm going to do it this way, delta EP, so the change in potential energy, or actually since they're losing potential energy, the loss in potential energy is going to be equal to the gain in the kinetic energy, in which our kinetic energy, to begin with, the initial kinetic energy is 0. So really, that's just equal to our final kinetic energy. And we know that the final kinetic energy has to be split amongst the two alpha particles. So it's 2 times 1/2 mass of one of the alpha particles, and it times the speed squared. Okay, so that's just 2 times the kinetic speed of the kinetic energy of 2 alpha particles. To find the potential energy here, it's the change, it's the negative of EP final minus EP initial, which actually makes a lot of sense because the final potential energy is smaller than the initial potential energy. So really, this is just equal to EPI minus EP final, okay? Which is equal to 2 times 1/2 mv squared. And really, these two just cancel out, to be honest. Okay, so let's fully write out the potential energies. The potential energy is going to be K, and what? This is 2 alpha particles? Okay, so that's just going to be K alpha. Alpha, I'm going to use alpha alpha. Really, alpha is, remember, the charge on an alpha particle is equal to 2 times the Coulomb, the elementary charge, which is 2 times the charge of a proton. Okay, 2 times 1.6 times 10 to the power negative 19. And this is over, the initial one is going to be closer, which is 2.5 times 10 to the power of negative 11 or negative 12. Negative 12 minus K, 2 alpha particles or charge on the alpha particles multiplied, divided by 0.75 meters apart. And this is going to be equal to m alpha v squared, since the 2's and the halves are canceled out. Okay, yeah, it's getting very messy here. So let's put in all our numbers, or let's calculate at least the left side first, just to make it look nicer. I have 8.99 times 10 to the power of 9, and my alpha particle is going to be 2 times 1.6 times 10 to the power of 19 coulombs. Since I have 2 of them, I'm going to say that squared. And you know what? I'm going to actually say it this way. This multiplied by 1 over, and I've done this in a previous example before, which is I just factor out these two on the outside. So I get K alpha alpha times in brackets 1 over 2.5 times the power of negative 12 minus 1 over 0.75. Okay, yeah, the math looks kind of ugly. It's not hard, it's just ugly, okay? So I'm going to calculate this first, just to get it out of my plate. So I get 3.68 times 10 to the power negative 16, and this is going to be the mass of an alpha particle times its speed squared. Do I have space over here? Hopefully. Okay, let's divide this here. And if I want to solve for the speed is going to be equal to 3.68 times 10 to the power of negative 16 here. Hopefully that number is right. Divided by the mass of an alpha particle. So I'll do that maybe down here. The mass of an alpha particle is composed of 2 protons and 2 neutrons. So the mass of a proton, let me just write this here. Mass of a proton, you can find in your data booklet, there it is, 1.673 times 10 to the power negative 27 kilograms. And the mass of a neutron is over here, which is slightly bigger, 1.675 times 10 to the power negative 27. Okay, oh gosh, so many details. 1.675 times 10 to the power negative 27. Okay, let's just calculate this out first. Okay, this is 6.696 times 10 to the power negative 27. So that's exactly what I have to put down here for the mass of an alpha particle. And since this is, let's put in some units, so that's kilograms, this is in joules. So for the speed, I have to take the square root here. So after I divide the 2 and take the square root, I finally get 2.34, which is going to round to 2 sig figs. So 2.3 times 10 to the power of 5 meters per second. Oh my god, that was a big question. Okay, you know what? Screw this. I'm gonna do 9 in a separate video. So, if you can bear my tiny writing, good luck. But I'm so sorry. Here it is. Next time, I'll make sure I get more space. Thank you for watching. Fan Mama Physics, signing out.